Dunny.
Salut, je m'appelle the Astro 30 and welcome back to AEL. I don't know why I'm talking French, but anyway. If you're new to this channel, please consider going down below and subscribing if you haven't done so already. That'll be great. Cheers, thank you very much. Today we're looking at this Amplifier project, experiment, whatever you want to call it, that I've been working on for the previous two videos. And in the last video on this, I managed to get the DC offset down to almost zero by playing with the 560 ohm resistor value in the VAS circuit, and I found around about the 360 ohm mark was correct. However, there's a problem with that. There's the VAS transistor there, that's a BD139 now. I was having issues with the TRP 41C and 42C respectively. I'll get to that in a minute. But it's now BD139. The problem with having the resistor value on the collector of the long tail pair that drives the base of the VAS here lower than the 560 ohms is bringing this base closer and closer to the negative side of the rail, and that would be the reason why when it was loaded into 4 and 6 ohms that power supply was going into current limit, even if the pots for the current set were set maximum, including when the speaker was turned on. We had that really loud mains type hum and then a pop. Well, that was the current limiting coming on here and staying on for a good, I want to say, 5 seconds, and then everything returning back to normal. So I didn't like that idea. I went back to the 560 ohm fixed resistor and got rid of the potentiometer. But we're going to explore another way that we can get rid of DC offset. And currently we're sitting around about 17 millivolts, positive DC this time, which is not bad. I mean, it was actually 30, more like 30 last night when I was messing around with it, but it seems to have gotten lower today. Don't know why. Okay, well that's an interesting camera position I've never tried yet. That's what she said. Anyway, it works. So I'm going to just demonstrate what I'm going to be doing. So this is our positive supply line of the power amplifier. This is our constant current source represented by that funny looking 8. And that is driving our long tail PMP pair. I'm really bad at drawing today. So on this side, that's the negative feedback side, and this side is the input with our ground reference resistor for this input transistor here. So this is currently 27k, 2k2 there, and this is currently 22k. Okay, and we come down on our collectors on the long tail pair to the 560 ohm resistor that I've got fixed in the circuit. This is the negative supply rail, so VEE. This collector comes directly down to the negative rail. So that's our long tail pair input circuitry. We've also got this 1k resistor here and this 100 microfarad capacitor, giving us our gain of 23 with these values. And this is controlling the frequency response of the amplifier. The lower this capacitance is, the less bass response you get out of it, I suppose would be a good way of describing it. And then off this collector here of the first transistor, we're going off to, well, our VAS transistor, which is in this case a BD139. That goes off to the drivers and the bias, and this terminates down here. Alright, well currently when I had just the 560 ohm resistor here and all this like it is now, we had a DC offset of approximately 60 millivolts, which seems pretty high, which it actually is. I found by inserting a small resistance into the emitter of the VAS transistor here, in this case I've now chosen a 68 ohm, well, now that DC is what we see it now. It's roughly, I'm going to say 20 millivolts, something like that. But it's still pretty high. So the other way, apart from modifying this resistor value, which is probably sometimes never a good idea, we can actually get the input stage to balance, which is what we're trying to do. The obvious choice would be to match these two input transistors so that they're perfectly matched. That is for its VBE and its HFE, like using a cheap transistor tester or whatever, part tester, which will give you the HFE value, and you match the two transistors HFE as close as possible. That's one way. The second way, and what is very important in any amplifier design, is that these two resistors here, or this resistor and this resistor in combination with this resistor, they have to be roughly the same value. So the resistance on this side has to equal the resistance on this side. And what I've done is I've temporarily got a trim pot in circuit set to roughly 22k, it's a 100k pot, in place of the fixed resistor. And if we vary the resistance of that resistor, we'll see some magic happen. That trim pot there, just in the center of the screen, that's the 100k trim pot. That's now in place of our 22k feedback resistor. And as we can see, measuring its resistance, currently we're around about 22k. And I've got the original 22k just hanging out here in the breeze. So I want to swap this back to its output. Make sure that doesn't short on anything. Disconnect that negative lead, connect it back to ground, and connect this other flying wire back to the base of the long tail pair on the negative feedback side. There we go. Make sure to set the meter back to voltage and not leave it on resistance when measuring output voltages, which I tend to do quite often, which doesn't make the amplifier very happy. Then I can apply the power. Nothing unusual. As we can see, there's roughly 20 millivolts of DC offset. Now if I start to rotate this pot clockwise, because of how I've got this configured, that will increase its resistance. We don't want to decrease the resistance. We want to get this resistance as close to what the input side is. So if I start rotating this pot, as we can see, the offset is coming right down until we come to a minuscule amount. And if I go over, it starts to go into the negative. So it's not an exact science here, but we've roughly got the offset now at 0 for all intents and purposes. So I'll kill the power. I'll go back to measuring across this trim pot for its resistance. I tell you, having clip leads on multimeter leads is a lot easier in some respects. There we go. Go back to resistance. About 24k. So it wasn't that far out actually, but yeah, I reckon I got good contact, haven't I? Yeah. So I reckon it should be more like a 27k on that side. If I remove this, put it back to its output, let's try that again. Put that back to ground. Well, I can take this trim pot out of circuit completely now. That was not what I wanted to do. And I'll put a 27k fixed resistor in. Okay, this place of that, take that out, that goes to that white wire. Fiddly. Very small. Well, maybe I'm just getting old. Get in there, you bastard. Right. Alright, the 27K is installed. Again, make sure to go back to voltage before applying power. Turn it on. And look at that. It's around about 8 millivolts minus. That is exceptionally acceptable. You wouldn't be able to probably get it any better. Well, you probably could get it better than that, but I don't see the point. Getting it down to close to zero is what the goal is here. So that's why balancing the input stage is very important. Having the same resistance on both sides. It keeps the DC offset relatively low. It just means now the gain is more like 28 instead of 23, but that's perfectly fine. Not much real difference between 23 and 27. Oh, sorry, 28. So why I have not changed the output drivers to the TIP 41 and 42C respectively? Well, my biasing circuit will not work with those transistors for whatever reason. I'm going to do a little bit more experimentation in a minute, but I got no adjustment with the bias, and I put the bias circuit back to as was in the original schematic, and it still doesn't work. And it doesn't work with the 1K trim pot and these drivers. So I left them as BD139 and 140 for now. The reason that the VAS transistor is now a BD139 is because the output drivers are the same type of case of transistor. Why have a TO220 as a VAS transistor when your drivers are a different case style? So I'm going to play around with the bias servo off camera and see what results I can come up with here. I know that looks weird, but that pot hanging up in the air now is a 5K linear normal potentiometer. That's now my bias pot, because I don't have a 5K multi-turn. So that's sitting where the trim pot used to be, and now I've got the original 2K2 resistor going from the base to the positive side driver, as it was in the original schematic. The series resistor has been removed. I'm measuring the voltage drop across that 100 ohm resistor, and currently we can see it's at 3.8 volt DC, which is a current of 38 mA. So if I adjust the pot without touching things too much, well, the lowest we can go at full anti-clockwise is 1 volt, which is 10 mA. As I rotate the pot slowly, after we start getting above around about halfway, it goes up. So the 1K was not going to work in that instance. Now we're at like 82 mA. If I go fully clockwise, 123 mA, something like that. So I'll back that back down to roughly 35 mA, 30 mA, something like that. That's good enough. And that's 38 now. Too far. That'll do. Either I drew that schematic wrong and put the wrong value for the trim pot, which is more than possible because I got the input stage transistors backwards. Plus I also got the VI limiter transistors backwards. Well, one of them. So it is probably quite possible that I have put the wrong value for the pot. It was probably meant to be 10K, not 1K. Yeah, as I say, it was in 2011 and I don't know what I was doing back then. I don't remember what I was doing last week, to be honest. So there's the bias servo sorted. I'm using a BC546 transistor instead of the 547. It has a much more smoother response when adjusting the current. Don't know why, it's just different HFP of the transistor, I guess. So I'm not going to make this video too much longer. I've sorted out the DC offset properly. The bias is now configured properly. I just want to know if I swap out these transistors to what they were supposed to be, whether it's going to affect the bias. Because when I was doing it last night, the current shot up to 230 mA and was non-adjustable. So I want to see if changing out those driver transistors makes a difference. With the transistors changed out, they're facing the other way in orientation to the original ones because the pinout is reversed. I haven't touched the bias pot, but we're now around about 100 mA. And this was the problem I was having last night. So I don't know if I can adjust that down. So I'll turn the pot. Oh yeah, I can. Okay, so 15 MA. So, yeah, okay. Correcting the bias servo is now working with those output transistors. I should say driver transistors, so that's perfectly fine. Yeah, okay. So that does still give me an option of a wider range of drivers, but as long as the bias servo is going to adjust down to a reasonable current level with the differences in driver transistors, that's perfectly fine. I'm happy with that. I want to know what the maximum current this will draw. Yeah, well, when it's maximum, it just goes to shit. And it doesn't know what voltage it actually is. So yeah, by the time I get to about halfway, it just goes all over the place. So I'll just quickly turn the supply off. I want to see what our DC offset is now with the different drivers in. It should be the same. I'll try and do this without disturbing my bias pot too much. Okay, turn the power back on. Seems to have jumped back up to 27 odd millivolts. Not sure why. That is interesting. Okay, I'm going to swap back to the BD13914 and readjust the current again, and we'll have another look at the DC offset. Okay, changed. Hardly anything apparently. So that's interesting. I'm not sure what exactly the deal is here, but I'm not complaining. A low DC offset is what we were aiming for in the first place. I'll just short out my resistor so we're getting the full supply voltage through and it's not limiting the current. Yeah, it's jumped back up to 10 millivolt. Okay, so it looks like for the design of the amplifier, the driver transistors are also a consideration. But I mean, even 20 millivolt DC offset is not that bad for a speaker, so, you know, you can get away with it, basically. Get away with it. So I'm quite happy now with how this is coming on. I'm not going to worry about the current mirror anymore. I don't see the point of the extra complexity. I mean, yeah, it has its advantages, but in this case, yeah, I'm going to leave it as it is. So I'm going to load it into 4 ohms with the power supply off, and then turn the power supply on, and I expect a different result than the last video where the power supply went into current limit and stayed in current limit for about 5-6 seconds, whatever it was, and then came back out of current limit. So let me just hook up the load. I've got to turn it off first. Load is connected at 4 ohms and I've got the multimeter still across the output. That's fine. Turn it on. Did not go into current limit. There you go. And across the load we've dropped to around about 8 millivolts. Well, actually minus 8 millivolts DC offset. It's not really that, you know, a concern anymore. And the good thing is, with all this messing around, we still have an output signal. Nice. What I'll do is, with an input signal, turn it off, and I'll wait a couple of seconds, and then I'll turn it back on and see what the power supply does. Bugger all. So yeah, changing that 560 ohm down to closer to 330 ohm was a bad idea. So this is beginning to look a lot like Christmas. No, this is beginning to turn into a viable amplifier circuit. Albeit there's a lot of modifications that have been done over the course of time. But that's just what happens when you're experimenting with things. The original design may not work the way you want it to, or the same. So some changes may have to be made. But I'm glad that the bias servo is a little less convoluted now and seems much more logical. With the input pair changed to BC556s instead of the 557s that were in there, our DC offset component is more like closer to 20 millivolts. So yeah, again, matching the input transistors for VBE and HFE is kind of important for a low DC offset. However, there is one other way we can get that DC offset to come back down, or at least balance the input stage. So here's what I propose to do. We've got our long tail pair, there's a hair on there. We've got our long tail pair transistors here, our PMPs. There's the 560 ohm resistor here in this collector, and that goes out to the VAS. That's our negative feedback in, and that's our non-inverting input side. What we could do is we can break the connection between these two emitters because they're currently joined together in the circuit. We can then split it off using two 220 ohm resistors back to the constant current source here, and we can insert this trim pot between the two emitters and an end here, with the center wiper going back towards the constant current source. And while we vary the resistance of this trim pot, what we are doing is we're changing the effective resistance of this resistor or this resistor, and that will effectively balance this input stage and bring our DC offset down. And this is a more conventional way of doing it, because with resistors in parallel, well, they're going to divide. So this pot, either side of this wiper, is a parallel resistance to either of these two 220 ohm resistors, and that will just lower each effective resistance or raise the effective resistance, obviously no higher than 220 ohm on one side and no higher than 220 ohm on the other side. If you were to bring the wiper close to this position of the potentiometer, well, this resistor is effectively shorted out, which won't affect the circuit operation. It just means you're going to have 220 ohm on one side and 0 on the other. And don't forget, originally these two emitters are joined anyway, so this resistor shorting out one of these resistors is not going to have that much of an effect. But if it's rotated fully counterclockwise or fully clockwise in any sort of like manner like that, well, as soon as power is applied, the DC offset may be quite high. Like probably, I don't know, I'd have to actually rotate the pot to its one full extreme end and see what the reading is. But we do this with measuring the output voltage between that and ground with the amplifier not loaded into a load, and we play with this pot and see what happens. So there's the 1K trimmer installed in the two 220 ohm resistors. The center of the pot is wired to, well, two ends of the 220s, and the other respective ends go off to either side of the pot and off to each emitter via some wires, and the center goes back to the voltage constant current source. So with the circuit turned on, we can see we've got roughly an offset of 15 millivolts, and I'm going to turn the pot in either direction to find out which reduces. I'm going clockwise currently, and I've got to let it settle between each turn, and it's coming down. So trimming those resistance values is changing the effective current going through each emitter junction of those input stage transistors, and we can get it down quite far. In fact, we can almost get it to 0. I could use a single turn pot, but trying to get this to adjust would be very finicky. But now we've got a DC offset of hardly anything, and yeah, that worked out brilliantly. So yeah, that little circuit there did actually correct our DC problem. So that's going to be included in the final design, I reckon, as well, just so it can be adjusted, because unless you've got a proper component tester or a curve tracer or something like that, trying to match the input transistors would be a difficult task. However, what I want to know is, when this is rotated till one of the end stops, what our DC offset is. I reckon about 200 millivolts, to be honest. Oh, it's gone up to 300. I don't think I've hit the end stop yet either. There it is. Okay, so at either end or the other, we're looking at 317 millivolts. So it wouldn't be a good idea to have the amplifier loaded first off to start with until you actually trim the resistor correctly. So I'm going to wind him back down until our offset comes back to 0, which would have been, I would say the pot is going to be somewhere towards the center of its position. So at least we know that either direction we can trim that offset, which is nice. So I need to get it back into the positive. And my screwdriver slipped. I'm getting close, actually. I'm not too far off now. For all intents and purposes, I'm going to say there. That's pretty close. I mean, it's not an exact science here. I do want to try and get that as close to 0 as possible. That's about right. Someone suggested in the comments to actually touch, like heat the input stage transistors with my finger to see if the effective DC offset would change, like lower or higher, just for academic purposes. So I'm going to touch transistors. It's moving around a bit. Not touching it anymore. Touch the other one. No, it doesn't seem to really be having that much effect on the DC offset component. So, well, at least with the heat of my finger, it's not really changing the DC offset characteristic of the circuit that great of a deal. So there, I've just gone and proved that one. So I'll reload the circuit, and nothing unusual happened. Make sure we're still getting a signal output, which we are. And in actual fact, it looks a lot cleaner. It was a bit hairy on top there. It was oscillating slightly, ringing. Adding in that trim into the long tail pairs emitters, or at least the series resistors anyway, seems to have cleaned that up a bit. So that's good. What I want to know is, for a final experiment, let's turn it off. I want to see if the current limiting of the power supply doesn't misbehave when turning it back on when it's loaded, like it did the other day. No. Excellent. Okay, so this amplifier is working reasonably well. Need to drop that voltage per division down so we can see it better. I'm getting to the maximum of my power supply, which is why it's starting to break up a bit like that, because current limiting is starting to come on. And with the modifications now at plus minus 16 volt, which is what it's dropped down to, we're getting 6.88 volt out, which is more closer to 12 watts into 4 ohms, but we've got to consider our supply voltages now, which are around about plus minus 16 volt. So yeah, that's to be expected. It's not on the full plus minus 35 volt rails, so it's still not bad really, considering the amount of changes that have been made. And yeah, that was getting mildly warm, but it is producing a signal, so that's good. So what I might do is I might hook the amplifier back up to a speaker and just see if we've got rid of that turn on transient that we had the other time, and then I'll end this video, because I'm not going to go into too much depth. I just wanted to go around and make some final modifications to the circuit that I'm happy with, and I'm now happy with the results that I'm getting. So I'm getting closer and closer to a valid design, which was my whole intended purpose behind this. And I don't really want to bore the shit out of everyone by just doing the same, experiment every single video, but yeah. Okay, so let me hook up a speaker and we'll see what happens. Speaker is connected, so I'll turn the power supply on. Well, there was an initial bzzz there when it first turned on, but that again is the power supply current limiting slightly when it starts, but that's fine. And with the oscillator connected, yeah, it's still noisy, but if I disconnect it, maybe disconnect the ground as well. Yeah, there we go. Noise went away. Ooh. Okay. So I'll run the oscillator. Yep. Still working. Excellent. So, that's going to be probably it for this video. I just wanted to touch on some changes to the design and try and make improvements on things, basically. Because yeah, I didn't like the original DC offset that it had, but we're now currently hovering around, even with the load connected, we're hovering around about the -2 millivolt mark, something like that. So it's perfectly fine. So I'll turn it off. Still no turn off transient, which is nice. Yeah, so I'm going to leave this video here, and if you enjoyed it, please remember to go down below, like, comment, subscribe if you haven't done so already. And as always, this is the Astro 3 saying see ya, have a great day.